So let's take a look at the solution to this problem. So what I'm interested in is what is the mass of just this inner part of the Earth? And we see that appearing right here in this equation. These two fractions represent the density of the Earth, and if we assume that it has the same density throughout, then they're equal to each other. So just a little bit of algebraic rearrangement, and the mass of the part of the Earth we're interested in is equal to the mass of the total Earth divided by the volume of the total Earth times the volume of the part of the Earth that we're interested in. So now what I'm going to do is I'm going to put in the formula for the volume of a sphere. So we still have the mass of the total Earth here. Volume of a sphere is 4/3 pi r squared. I'm using capital R here to represent the radius of the entire Earth. So I'm going to draw that over here. That's capital R. That's the radius of the entire Earth. Here we have the volume of just the part of the Earth we're interested in. So that's 4/3 pi little r squared. And so that would represent that distance right there. And of course, I made a mistake. These should both be cubed because that is the formula for the volume of a sphere, 4/3 pi r cubed. Sorry about that. I'm going to cancel out the 4/3. I'm going to cancel out the pi's. And so what I'm left with is the mass of the entire Earth, m total, times the radius of the part of the Earth we're interested in cubed divided by the radius of the entire Earth cubed. That is the mass of the part of the Earth that is underneath the person's feet. We had a person in a well here. And so that's the mass that we need to put in. This expression is what we need to put in for the mass of the part of the Earth that's attracting the person into this equation. So let's see what that looks like. So the force of gravity acting on this person is capital G, and then I need to substitute this in. The mass of the total Earth, and maybe I'll bring the mass of the person over here next. And then from this expression, I had little r cubed. And then divided by, from this expression, there's a little r squared. And from this expression, there's a big R cubed. And by the way, this little r squared that's in this expression is, in fact, the little r that's in our picture here. This is the distance between the centers of the two objects that you're trying to find the force between. The distance between the center of the Earth and the distance between the person, which definitely is little r. So this little r is the same as this little r right here. That means that r squared will cancel out the cube right here. And so we can simplify this expression a little bit. G times the total mass of the Earth divided by the total radius of the Earth cubed, that factor multiplied by just the radius from the center of the Earth to where the person is. And I forgot a mass of the person in there as well. Sorry about that. But I'm going to cancel that out in a moment. I'll show you how. Because what I'm really interested in is the acceleration due to gravity that this person experiences. And just a reminder, the formula we would use to calculate that, the force of gravity acting on this person is equal to the mass of the person times the value of g wherever the person is. So I'm going to replace this force of gravity with this expression for the force of gravity. So we have the mass of the person times the g wherever they happen to be is equal to g m total mass of the Earth, over total radius of the Earth cubed times little r times the mass of the person. And as I said, mass of the person was going to cancel out here. So here's our final expression. This is what we were looking for. This was our goal. That the acceleration due to gravity, if you are in a well inside the Earth, is equal to g times the mass of the total Earth divided by the radius of the total Earth cubed times the distance between where you are and the center of the Earth. That is the final answer to this question. Now, before we're done here, let me ask you to think about this. This is a very common follow-up question on the AP test. And that is, if you were to make a graph of how big the acceleration due to gravity is as a function of how far you are from the center of the Earth. So 0, that's the center of the Earth. And we're moving outward now, away from the center of the Earth. At some point, you're going to pass the actual radius of the Earth. And then eventually, way out here is going to be infinitely away from the Earth. So again, think about what this axis is. Here you are at the center of the Earth, further from the center of the Earth, further from the center of the Earth, further from the center of the Earth. Finally, you hit the surface of the Earth right here, and then you continue to get further and further and further from the Earth until you're actually out at infinity. The question is, what does the acceleration due to gravity look like as you go along that distance? I'm going to draw that for you in one moment, but why don't you pause the video and see if you can figure out what that's going to look like on your own. Pause it now. Okay, you're back. I hope you were successful with this. So as you go from the center of the Earth out to the surface of the Earth, this is the equation that determines how big the acceleration due to gravity is going to be. What I want you to notice is that the acceleration due to gravity is directly proportional to how far you are from the center of the Earth. None of these numbers are changing when you're inside the Earth. So to plot a direct proportion, we draw a straight line. So the acceleration due to gravity simply increases as you go away from the center of the Earth in a linear fashion. Now, once you get outside of the Earth, now we don't have to do any kind of a strange mathematical manipulation to figure out how much of the Earth is attracting you. It's the entire Earth that's attracting you once you're outside of the Earth's surface. So we're back to this equation. F equals g m of the total Earth times, the mass of the person divided by how far away you are from the Earth, the center of the Earth, and that gets squared. And so the relationship now, and I know this is force of gravity, but it's the same thing for acceleration due to gravity. The relationship now between the force or the acceleration due to gravity and how far you are from the center of the Earth is an inverse squared relationship. Inverse means you're going to dive like this and curve like this, and it's hard to really draw the difference between inverse and inverse squared, but that's the basic shape. So that's what they would be looking for as the answer to that question.